In the previous lesson, we covered the first 5 properties of Fourier series coefficients: linearity, time shifting, frequency shifting, conjugation, and time reversal. We also discussed conjugate symmetry for real signals. In this lesson, we complete the property set with properties 6 through 11: time scaling, periodic convolution, multiplication, differentiation, integration, and Parseval's theorem. We will also prove the periodic convolution property and Parseval's theorem using orthogonality. Property 6 is time scaling. If we compress the signal by replacing t with a t, where a is greater than 0, the Fourier series coefficients remain the same, x of k. However, the fundamental period changes from t to t over a, and the fundamental frequency changes from omega 0 to a times omega 0. So the coefficients stay the same, but the harmonics are spaced further apart. Property 7 is periodic convolution. The periodic convolution of x of t and y of t, defined as the integral over one period of x of beta times y of t minus beta d beta, has Fourier series coefficients t times x of k times y of k. Notice the factor of t. Periodic convolution in time corresponds to multiplication of coefficients scaled by the period. Property 8 is multiplication. If we multiply x of t and y of t in time, the Fourier series coefficients are the discrete convolution of x of k and y of k, written as the sum from L equals negative infinity to infinity of x of L times y of k minus L. This is the dual of property 7. Multiplication in time corresponds to convolution in frequency. Let us prove property 7. Define z of t as the periodic convolution of x of t and y of t. That is, z of t equals the integral over one period of x of beta times y of t minus beta d beta. Both x and y are periodic with period t. We substitute the Fourier series expansions. X of beta equals the sum over k of x of k times e to the jk 2 pi over t beta, and y of t minus beta equals the sum over m of y of m times e to the jm 2 pi over t times the quantity t minus beta. Substituting into the integral, z of t equals the double sum over k and m of x of k times y of m, times the integral over one period of e to the j times k minus m times 2 pi over t times beta d beta, times e to the j m 2 pi over t times t. Now we use the orthogonality result. The integral of e to the j times k minus m times 2 pi over t times beta over one period equals t when k equals m and 0 otherwise. This eliminates the inner sum. Only the terms where m equals k survive. So z of t equals the sum over k of x of k times y of k times t times e to the jk 2 pi over t times t. Comparing with the synthesis equation, we identify z of k equals t times x of k times y of k. This completes the proof. Property 9 is differentiation. The nth derivative of x of t has Fourier series coefficients equal to jk omega 0 raised to the nth power times x of k, where omega 0 equals 2 pi over t. Each differentiation multiplies the kth coefficient by jk omega 0. This amplifies high-frequency components and suppresses the dc term since the coefficient is 0 when k equals 0. Property 10 is integration. The integral of x of t from negative infinity to t has Fourier series coefficients x of k divided by jk omega 0 valid for k not equal to 0. For this to be finite-valued and periodic, we need the DC component x of 0 to equal 0. If x of 0 is non-zero, the integral grows without bound and is not periodic. Notice that differentiation and integration are inverse operations in the frequency domain. One multiplies by jk omega 0, the other divides by it. Property 11 is Parseval's theorem. It states that the integral of the squared magnitude of x of t over one period equals t times the sum of the squared magnitudes of all coefficients. That is, the integral over t of the absolute value of x of t squared dt equals t times the sum from k equals negative infinity to infinity of the absolute value of x of k squared. This relates total signal energy per period to the energy distribution across harmonics. Let us prove it. We write the absolute value of x of t squared as x of t times x star of t. The Fourier expansion of x of t is the sum over k of x of k times e to the jk 2 pi over t times t. For the conjugate, we use the fact that e to the j theta conjugate equals e to the negative j theta. So x star of t equals the sum over m of x star of m times e to the negative jm 2 pi over t times t. Integrating the product over one period, we get the double sum over k and m of x of k times x star of m times the integral of e to the j times k minus m times 2 pi over t times t dt. By orthogonality, the integral equals t when k equals m and 0 otherwise. This leaves the sum over k of x of k times x star of k times t, which equals t times the sum of the absolute value of x of k squared. This proves Parseval's theorem. Let us summarize all the properties covered in this lesson. Timescaling preserves coefficients but changes the period. Periodic convolution in time gives coefficient multiplication scaled by t. Multiplication in time gives discrete convolution of coefficients. Differentiation multiplies coefficients by j, k omega 0 to the nth power. Integration divides coefficients by j, k omega 0 requiring 0 dc. And Parseval's theorem connects time domain energy to spectral energy. Together with the 5 properties from the previous lesson, these 11 properties form a complete toolkit for analyzing Fourier series without computing integrals directly. In the next lesson, we begin deriving the continuous time Fourier transform from the Fourier series.